for textual synopsis generation for videos. So here we want to answer one question. We want to find out how we can make browsing video summaries even easier for the user. Our answer was to generate text summaries for the videos. It's fairly easy to read a short textual report about a video to understand what happened in it, and we can also use natural language to search within that content to quickly find relevant information. There is a naive approach to do this. So we have the video. We can use any existing off-the-shelf video summarization technique to summarize it and select some shots, and then pass it through a video-to-text network or a video caption generation network to come up with a text summary. There are a few issues with this kind of approach. If our video summarization is imperfect, meaning that it may select bad or repetitive shots from the video, this error will be amplified throughout the text generation. After all, it's a challenging task to generate textual descriptions for egocentric videos. So we propose an alternative approach, which is kind of in reverse order. We take the video, we break it down to short shots, we pass the shots through a video-to-text generation, so we create a very long textual document, and next we use a text summarization framework to summarize this long text to come up with a summary. The advantages of this approach is because essentially we first generate as much text knowledge as possible. Some of these descriptions may be correct, some may be wrong. We can try to identify which ones are correct, and from the correct ones we can select the most representative ones. So to show you the framework, we take the video, we break it down into shots, we sample a few frames from each shot, we pass the frames through a 2D CNN for feature extraction. We can use any feature extraction backbone here. The visual features extracted at this point will be passed through a caption generation network that is consisting of encoder and a decoder. This part of the network will produce a description. We take the visual features and the textual description and pass it to a visual language content matching unit in order to identify whether the generated description is correct or not. Next, we have a Purport network that tries to essentially read all of these generated descriptions, and from the correct ones, it wants to identify which ones are representative and need to be included in the eventual summary. Our Purport network assigns a representativeness score to each of these descriptions or video shots. Also, we get some confidence scores from our visual language content matching unit. The product of these two will result into impact score for each of these descriptions. Our caption generation network has a temporal attention module that essentially is trying to find which of these visual features are useful. The reweighted features will go through an LSTM-based encoder-decoder to produce a caption for the shot at hand. We use a standard captioning loss to train this part of the network. Our visual language content matching unit takes as input the visual features of a certain clip, video shot. It processes them into a final representation using a bidirectional LSTM. It also takes as input the generated description using the caption generation network at the previous component. It also produces a final representation for this description. The product of these two descriptions will form a visual language feature for that specific clip. This feature is passed through a fully connected layer that assigns a confidence score whether this description is correct or not. The visual language feature is copied for further use in Purport network. So since at this part of the network we are trying to determine whether a description is correct and matching the visual content or not, we are employing a binary classification objective binary cross-entropy loss at this part of the network. In our Purport network, we've taken all the visual language features that we could generate using our previous component. We process them using a bidirectional LSTM, and a fully connected layer assigns a representativeness score to every single clip in a way. We also, at this point, we want to find out whether a description has to be included in the summary or not. So it's a binary classification problem. Another binary cross-entropy objective is introduced here. Here's the entire framework all together in one slide. We train this network in an end-to-end manner by combining all the objectives together. In our experiment, we used the same UT egocentric dataset. This dataset has been annotated densely with textual annotations. We evaluate our model both in visual domain using the area under the curve metric that we introduced in previous chapter, and also in the text domain using Rouge, Blue, and Meteor. These are the most commonly used metrics in natural language processing. To compare our model with state-of-the-art video summarization techniques, we took those, we accompanied them with a video caption generation network identical to ours, so our method is not an advantage compared to them. And here's the performance that we could get for all the baselines that we could find. When we compare our model with the existing work, we see improvement pretty much at every metric. We wanted to find out why our method is doing better, so we ran a few experiments. So our intuition was that our model will do better because there will be a lot of noise in the generated descriptions. So to do this, to actually confirm this, we took the videos and we discarded everything. We just kept the caption generation network. The idea here is to take the video and generate as many sentences as we can about that video and then evaluate the performance. So here are some of the descriptions that the video caption generation network could produce. As you can see, some of the descriptions are correct. Even though they don't match the actual ground truth description, they are correct in describing what is happening in the video. Some other captions are correct in the sense that the sentence is meaningful. However, it's not describing what is happening in the video clip. And the second type of error is where the sentence does make no sense at all. We evaluated the performance of the video caption generation alone and, using Rouge metric, and as you can see, the numbers are not all that high. We also performed some ablation study to do a component-wise analysis to make sure that every component that we are introducing is being helpful. This ablation study is mainly concerned about the visual language content matching unit and the Purport Network. So we should remember that the full model performed 17.33 using Rouge metric. When we completely remove the visual language content matching unit, we see a major drop in the performance. If we keep the visual language content matching unit, however, we discard the auxiliary loss that we were using to train it, we see a drop in performance, however, not that much. If we completely discard the Purport network, we also see a rather noticeable drop in performance. This is because we need to know what happened in the entire video to be able to select the most representative one. And finally, for the sake of completeness, we generated caption for all the shots in the video and use a text summarization approach, state-of-the-art text summarization approach, to summarize this long document into a text summary. And as you can see, the performance of such model are not good whatsoever. We also evaluated our model in visual domain. So here's the performance that we could get using area under the curve that we introduced earlier for the baseline. Comparing those approaches to ours, we see improvement even in the visual domain, even though that was not a concern. Here's one qualitative result. So this is a textual summary that the method has generated. The original summary had 144 sentences, so I cut it short so I can fit it in the slide. But you get a sense of what it would look like to produce a textual description.